Hello, welcome back. We are looking at polymeric biomaterials and we are now looking at the theme of temperature and solvent effects since the last lecture. And in today's lecture, we are going to be looking at solution thermodynamics. Now, note that this represents a bridge between the previous lecture where we looked at polymer solutions and the next lecture where we will look at the Flory-Huggins theory to understand the thermodynamics of polymer solutions. So, in this lecture, we will lay the foundations to understand thermodynamics and free energy of mixing in general, and we will postulate what we will call an ideal solution of small molecules, which will later form the basis for us to understand the Flory-Huggins theory for polymer solutions in the next lecture. So, in today's lecture, we are going to be first contextualizing thermodynamics against concepts we have seen earlier and concepts that we will see in the next lecture. We will also look at the contributions of a few important scientists to this field, and then we will recap a little bit of some of the key concepts involved in thermodynamics, namely Gibbs, free energy and chemical potential, and then we will define the criterion for thermodynamic equilibrium, which many of you may be familiar with if you have already taken some kind of a course in thermodynamics. And as you might be aware, it will have two different contributions, namely the enthalpic and the entropic contributions. And ultimately, we will develop the framework for the ideal case where we will look at ideal solution for small molecules. So, let us first contextualize solution thermodynamics, first looking at what we have looked at in the previous lecture, namely lecture 14, where we have looked at polymer dissolution. So, just to recap, we saw that dissolution was a slow and a multi-stage process. Unlike for small molecules, for polymers it is a very slow and process that involves multiple steps. Some key steps include solvent diffusion, polymer swelling, plasticization, uncoiling of chains, solvation, all of these factors we have seen. You have, more importantly, disruption of secondary bonds between the chains as the solvent penetrates. Then you have chain mobility and eventual entanglement where the polymer chains go into solution. And at the bulk level, we saw that as you increase the polymer concentration in solution, you will see changes to bulk properties, one manifestation of which we saw was viscosity. Now, what we are going to look at in this lecture is to understand the thermodynamic aspects of polymer dissolution. So, when you add a polymer to a solvent and you say that a solution is formed, what is actually happening from a thermodynamic perspective? And like I said, in this lecture, we are not going to be really focusing on polymers themselves. We are going to be looking at small molecules as a starting point, set up the ideal case, and then in the next lecture, extend that phenomenology for polymers with appropriate modifications to look at what we will later call the Flory-Huggins theory. So, that we will do in lecture 16. But why is this even important? Why is solution behavior even important to look at? So, understanding solution behavior, as we have already seen, is important for many characterization techniques that we have already seen. And for polymeric biomaterials, a lot of the materials will be used in aqueous media, right? So, there you will see effects of solvents coming in. Later in the course, we will look at something called hydrogel swelling. We have alluded to it before, where you take a cross-linked network, a hydrogel that swells in water. There we will have to resort to a theory called the Flory-Renner theory or the Merrill-Pepper's theory, which is a modification to the Flory-Renner theory, and the basis for that will be the Flory-Huggins theory, right. So, if we have not understood Flory-Huggins and the basis for that well, we can't handle the thermodynamics of hydrogel swelling very well. So, this is also another reason why we have to look at this. If you have blends or composites, then thermodynamics can tell you something about the phase behavior of such systems. We have also looked at stimuli responsive behavior earlier, where we talked about the example of poly-NIPAM, where above and below the LCST, you will see different kinds of behavior for the chains, and that can be explained using thermodynamics. Even things like polymer degradation and biomaterial processing are areas where thermodynamics plays a very important role. So, thermodynamics is largely ubiquitous in many of these processes and systems, and thus contextualizing solution thermodynamics to understand solution behavior is important for us to make further progress in this course. And before we delve into the nitty-gritty of this topic, we will first take a quick but what I think is a very important digression. And this is to look at the contributions of three important people to this field. One of them is Gibbs, the second is Boltzman, and the third is Flory. Now, this is obviously just a very small subset of people who have contributed to this field. The number of scientists who have contributed are enormous, but we will look at these three people particularly and quickly look at their contributions and see what we can learn from them as a means to pay our homage to the type of work that they have done, and the fact that we are able to now deal with these systems so well today is because of the foundations that these great men have laid in the past. Every now and then, science will throw up one scientist whom we would call a scientist, and Gibbs was one such scientist. Gibbs was a remarkable gentleman, and I can only cover a little bit of his life and his contributions in this lecture, and I would strongly encourage you to go and look up his biographies, particularly by Charles Hastings, which you can procure and read about his life. Now, Gibbs, we think of him as a scientist because the scientists that we admired Gibbs. So, for example, Einstein is said to have remarked that Gibbs was probably America's greatest minds, and Van der Waals, for example, in his Nobel address refers to Gibbs's contributions and how that led eventually for Van der Waals himself to make further progress. Maxwell, who was another scientist that we all look up to, he is one of those few people whom Gibbs corresponded with, and he immediately understood the genius that Gibbs was, and the correspondence between them is very interesting to note. You should look up that and get inspired by that. Gibbs was started off with doing some experiments, but after the 1870s or so, he completely switched to theory, and he published three seminal pieces of work. One of them was a geometric approach to thermodynamics, in which he first introduces the idea of free energy, and then he puts out another work on the phase equilibria of heterogeneous substances, and in that he introduces the idea of chemical potential. And in the last one, which is just elementary principles of statistical mechanics, which is published right before his death, he introduces the entire field of statistical mechanics as we know it today. So you see, just in that period, over 40 years or so, or maybe even less than that, he put out only these very dense terse treatises in which he developed new fields and changed the way we think about thermodynamics. And Gibbs also was a scientist who was not interested in self-promotion. So while Maxwell knew his contributions, understood the value of Gibbs's scientific work, Maxwell died early, and so Gibbs didn't have a champion until much later when his work started getting a lot of recognition. Gibbs was also a very self-contented man, and these are some lessons that we can learn from these great gentlemen. So Gibbs, except for a brief period when he visited Europe, he never left the New England area in the US, and he spent most of his life at Yale University. And for a large part of that period, he was not even given a salary. And when Hopkins decided to attract him with a salary, Yale countered with a salary that was lesser, and Gibbs decided to stay back. So we learn a lot from these great gentlemen, both the work and the life of these great gentlemen. Gibbs in particular is someone who is probably not as celebrated as some of the other scientists, but requires no less admiration than the admiration that we give to Newton, Maxwell and Einstein. So, we will look quite a bit at Gibbs's contributions in today's lecture. The other person we are going to be looking at is Boltzmann, who was an Austrian scientist. Shown here is a picture of his tombstone with an equation here, which is famously called the Boltzmann equation for entropy. Boltzmann's primary contribution again was to the field of statistical mechanics, and his primary idea was to investigate entropy from a statistical mechanics perspective, or keeping the premise that matter is made up of molecules. So, the molecular picture of thermodynamics, a lot of it we owe to Boltzmann, particularly his interpretation of entropy. And Boltzmann also contributed significantly to kinetic theory of gases. So, you might have heard of the Maxwell-Boltzmann distribution, for example. You might have also heard of the Boltzmann constant, which incidentally Planck named after him. Boltzmann, at that point in the late 1800s, it still wasn't well established that matter was made up of atoms and molecules. The molecular nature of matter wasn't as well established in that period. And the thermodynamic laws, while they had been established, didn't require you to assume the molecular nature of matter. So, Boltzmann ran into a lot of issues trying to convince people of his theories. In particular, he had issues with this another scientist, Mach, of the Mach number. So, these are very interesting periods in history where you see how science has progressed, but then theories get refined, evolved with time. Eventually, Boltzmann he led a very interesting life, but died a very tragic death. He committed suicide ultimately. Anyway, I mean, I think what's important to keep in mind is our understanding of statistical mechanics largely comes to us from Gibbs and Boltzmann. And Flory is to polymer, so he would be considered the spiritual successor in some sense of both these gentlemen for polymers. So, Flory started his career in DuPont with Carothers, whom you might remember from an earlier lecture about nylon. So, Flory was mentored in the initial days by Carothers, and then his career just took off, and he looked at, he developed the theory of polymer solutions as we know it today. He contributed significantly to many of the concepts we have seen in this course, including crystallization, polymer crystallinity, melting, rubber elasticity. I mean, you name it, he has contributed to it. And a large part of what we understand about polymer physics today comes to us from Flory. And if you just want to get a sense of how great these people were, you just have to go look up the number of equations or the number of concepts named after people like Gibbs and Flory. Just that list will be mind-boggling. And the reason we are taking this digression is because thermodynamics is one of those areas where historical perspective is very, very important. This is true for any course or any subject matter that you read, but particularly for thermodynamics it's very important because the concepts that we have today, with so much sophistication that we have today in terms of our facilities, in terms of technological advances, these people back in the day didn't have. And you really marvel at their genius, at how could they come up with these kinds of concepts when they didn't even have access to 1/10 of the sophistication we have today. So, we tend to have a much larger appreciation for their contributions. So, my hope is you will be inspired by the life and work of some of these great people. Go read more about them and understand their passion for science. For many of these people, science was not just the means, the science was the end also. So, their passion for science was manifested in the fact that while they were pursuing science, the pursuit itself in some sense led to an end where understanding a system or a process or achieving a result that shed new light that was unknown so far in itself was the reward. The rewards didn't come later. So, these are lessons we can learn from the lives of these great men. So, now that we have looked at very briefly these great gentlemen, we will now move on to the real topic of this lecture, which is Gibbs's free energy and chemical potential. So, like I said earlier, in his treatise, A Method of Geometrical Representation of the Thermodynamic Properties of Substances by Means of Surfaces, where Gibbs introduces a very interesting approach to understanding thermodynamics, a geometric approach. He defines something called free energy or the available energy in a system. Now, this word free has some historical baggage. So, you have to realize that thermodynamics had its origins in the era of steam engines, and then people were obsessed about converting heat to work. And so, what amount of heat was available for work, or what amount of heat was freely available for work, was something that was a constant preoccupation for people in that period. So, the word free simply means that it is the energy available or the for non-PdV work or non-expansion work. So, like I said, Gibbs's energy or free energy change, and notice that we are talking about change here, because in thermodynamics very often we are not interested so much in absolute quantities, especially in classical thermodynamics. We are more interested in changes in these quantities which are measurable. Thermodynamics, as abstract as it might sound, is largely interested only in quantities that are measurable. So, if the change in Gibbs energy is measurable, then we are interested in it, and it turns out that that has a very practical value also for us. In essence, it is the maximum amount of non-volume expansion work, this could be electrical work, osmotic work, etc., that can be extracted from a closed system at a fixed temperature and pressure. In other words, it is the thermodynamic potential that is minimized when a system reaches chemical equilibrium at constant temperature and pressure. So, notice that we are using, we are trying to define what free energy is or free energy change is, and we are connecting it to potential and equilibrium. And note that this maximum amount of work refers to non-PdV work, some examples of which are shown here. Now, with that as the basis, we can now look at what we would call the fundamental equation, complete fundamental equation in thermodynamics. Now, if you are not familiar with these kinds of equations, I would suggest that you go back and refresh some of your thermodynamics. Although we will not need these equations per se to move forward, it will always help if you have a deeper appreciation for these kinds of equations as you move through this course. The total differential for the Gibbs energy is given by this equation, and there are broadly three contributions if you want to think about it that way. One is partial with respect to temperature, another is a partial with respect to pressure, and the third is a partial with respect to composition or number of moles. So, the temperature dependence of for the free energy will give you entropy. So, this term will give you minus S. The pressure dependence here will give you volume, and the composition dependence will give you what we call chemical potential or partial molar Gibbs free energy. This is called chemical potential. Sometimes you will see it written this way. Now, this was a very important development that Gibbs came up with, because now chemical potential now became a very important idea for us to deal with when we talk about equilibrium. Even today, when we talk about, for example, diffusion of molecules, we say that molecules will diffuse until the chemical potentials are equalized. So, when the chemical potential of that component in phase A and phase B are the same, then the system has reached equilibrium. This is an idea we use even today, and that the starting point for that comes to us from Gibbs. And in Gibbs's own words, the way he defines this is, if to any homogeneous mass we suppose an infinitesimally small quantity of any substance is added, the mass remaining homogeneous and its entropy and volume remaining unchanged, the increase of the energy of the mass divided by the quantity of the substance added is the potential for that substance in the mass considered. Now, it might seem like a slightly complicated way to say it, but this is the most correct way to say it. And what he is really saying is, you can represent this by this again. So, what this simply means is, these terms here represent the temperature dependence, pressure dependence and the composition dependence. And in composition dependence, what we are doing is, we are keeping T and P constant. So, when we write it this way in this notation, whatever is put here is remaining constant when the other variable is changed. So, when temperature is changed, P and N remain constant, here T and N remain constant, and here T and P remain constant, and everything other than I remains constant. So, that is what we mean by N j not equal to I, because I is being changed here, all the other components are fixed. So, this simply is another way to represent the chemical potential in terms of U, which is internal energy. You can do the same thing with enthalpy, you can do the same thing with Helmholtz free energy, and you can show, depending on what you keep constant and what you change, the chemical potential can be defined in terms of either G or U or F or H. And so, that is what we are showing here. So, you see that when we are defining chemical potential in terms of, this is again chemical potential, in terms of U, S and B remain constant. And the reason why we are interested more in Gibbs free energy is because for chemical engineers, largely, we are interested in processes that occur at constant temperature and pressure. So, G happens to be the natural variable of interest for chemical engineers. Now, using this, can we now come up with a criterion for equilibrium mathematically, and from there can we now ask what processes are favored thermodynamically, what processes will not be favored thermodynamically. This is something that you might have already seen in other courses. So, at constant temperature and pressure, any change, so for equilibrium, G has to be minimum. There cannot be another state with a lower free energy if the system has already reached equilibrium. That is what it means. So, dG is 0 at equilibrium, of course temperature and pressure being constant, or in other words, no further changes are allowed in chemical potential. So, this is very important in the biomaterial context. It is very important in processes such as hydrogel swelling, where we will revisit this concept again and look at it in more detail, and also in things like solvent diffusion or even drug diffusion. Now, the real question we want to ask is, because we are looking at solution thermodynamics, the real question we want to ask is, how do we use all this knowledge to come up with some tangible criterion for mixing? So, if you are taking a solute and a solvent, we are not looking at polymers just yet, we are looking at a solute and a solvent. For them to form a solution spontaneously, if you want to use that word, the system should tend towards minimizing free energy G, or the change in Gibbs free energy has to be negative for this to occur spontaneously. So, this is something that you might have seen in courses that you would have taken based on thermodynamics. So, the spontaneity of change, or the more correct scientific way to say that, is thermodynamically favored process is given by the change in Gibbs energy being negative. That is what we would call a thermodynamically favored process at constant temperature and pressure. And when there is no change, further change possible in Gibbs free energy, the system has reached equilibrium. So, these two have to be connected, and if the change in Gibbs free energy happens to be positive, then that is not a spontaneous process, or that is not a thermodynamically favored process. So, all we have said so far is we have done two things. One is we have seen the connection between Gibbs energy and chemical potential, and we have seen different manifestations of the different types of free energy. So, for example, Helmholtz energy, enthalpy, internal energy, and how all of those can be used to define chemical potential based on what you keep constant and what you change. And we saw that the natural variable for us is Gibbs free energy. So, in some sense, G is like a master variable. with this one variable now, it is so powerful that we can use it to determine the direction that a system will take spontaneously based on whether the change in free energy is positive or negative, and based on that we can determine whether it is thermodynamically favored or not. In this case, we are looking at the specific process of mixing of a solvent and a solute. The second thing we have looked at is this criterion for equilibrium, this, based on which we can now relate it to this famous equation, which simply comes to us from Gs H minus Ts, which is another very famous equation that you all might already be aware of. Now, if you apply it to the specific case of mixing, then delta G submix is delta H submix minus T delta S submix, and for mixing to be thermodynamically favorable, this quantity has to be less than 0. There are a couple of things to note here. One is, there are enthalpic and entropic contributions to the free energy of mixing. You have temperature dependent effects, and as always recall that Gibbs free energy does not involve PTV expansion work, it is other types of useful work that we are talking about. Essentially, no volume changes allowed. So, now we will look at the enthalpic and entropic terms in more detail, first qualitatively, then we will quantify this. We will come up with a framework to quantify it. So, we will first deal with it qualitatively. The enthalpic term is one way to think about it, is to think about it in terms of the interactions between the polymer and solvent through intermolecular forces, or you are comparing and contrasting polymer-polymer, solvent-solvent interactions in the unmixed pure state versus polymer-solvent interactions in the mixed state. So, earlier we talked about, when we looked at solubility parameter in lecture 14, we talked about like dissolves like. Here we will redefine that a little bit. One with greater intermolecular forces excludes one with less favorable intermolecular forces. So, a component with greater intermolecular forces excludes the other with less favorable intermolecular forces. Now, if the polymer solvent interactions are favored, if the during mixing as compared to polymer-polymer or solvent-solvent interactions, then the enthalpy contribution will favor mixing. So, that is sort of what we are saying. So, this is a more explicit way to think about like dissolves like, where we say that the one with the greater intermolecular forces excludes the one with less favorable intermolecular forces. Also note that we have already looked at this in terms of the solubility parameter in lecture 14. So, now is a good time to pause and recall this, where we related to the solubility parameter to the square root of the cohesive energy density, which is given by this. And in that lecture, I would have asked a question where this simply represents the energy of vaporization, if you will, going from taking the system from the liquid state to the vapor state. Now, while you can easily think about this in physical terms for small molecules, for polymers, I would have asked, how do you contextualize this? Because polymers do not vaporize and form vapor. You can't think of PLGA vapor, for example, when you heat it. So, how do you determine things like this? If you have indeed gone back and looked up, you will be able to relate very well to what I am going to say next, which is, it is done using what we call a group contribution method. Broadly, the idea here is, if you have a polymer and you have different groups, which can be smaller parts of the large molecule, then the total system itself, the total polymer itself can be thought of as the contributions coming from the individual groups themselves in proportion to the number of groups such exist, and that is literally what this equation is telling you. So, delta here is related to Fi, where F is the molar attraction constant for group I, where I could be any group, it could be methyl, it could be benzyl, depending on what polymer you are talking about, and Ni is the number of such groups. If you have multiple benzyl, then you will have to account for those many numbers using Ni, and you sum over all that. Rho 2 simply represents polymer density and m is the molar mass. So, from this equation you can now access delta, which is the solubility parameter for the polymer itself. I will leave it to you as an exercise to convince yourselves based on the units here that you will get back the units of cal per centimeter cube to the half for delta. So, you can actually do this piecemeal, where you can find the Fi for each of those components in the chain, and you look at the number of such components in that chain, you multiply them and sum them up, and then if you factor in the density and the molar mass, you can indeed access the solubility parameter for a polymer. This is just one way to do this. So, from this you can see that delta H for mixing can be given by this equation, where you can relate it to the solubility parameters. So, this is an equation we have already seen in the earlier lecture, lecture number 14. Now, having looked at the enthalpic term in the free energy of mixing, we will now move our attention to the entropic term, which is which we will have to grapple with, because no amount of analogies will help, because every analogy I give for entropy will be limited in some sense. So, we will have to just keep repeatedly looking at these terms again and again, and eventually develop a reasonable understanding of what entropy means for our own selves. So, each of us has to be convinced about what entropy means, and what we can do here in a lecture or a course like this is to only point you in the right directions. Now, firstly, note that in this context we are talking about entropy from a molecular perspective. Where we are saying that it relates to the number of microscopic arrangements in which molecules of a system can exist for a given temperature and pressure in the macro state. Now, this was one of the key reasons for which statistical mechanics developed, which is to be able to connect macroscopic states, PBT of a system for example, to microscopic configurations. While classical thermodynamics did a very good job of explaining all the macroscopic properties, the molecular picture was missing, and that and as science started to understand that matter was made up of atoms and molecules, now you had to have a basis or a platform that could relate everything we saw at the macroscopic level in the macro state for a given temperature and pressure, let us say PV, PBT, these kinds of properties, relate them to what happens in the molecular level. That is what statistical mechanics provides us with. And entropy from that perspective is given by the Boltzman equation, which we saw at the beginning of this lecture, which was inscribed on this tombstone, given as S, which is equal to K times log of omega. Sometimes you will see log of W also, they are both equivalent. What S is represents here is the entropy, K is simply the Boltzmann constant, and omega here represents the number of possible distinguishable microscopic spatial arrangements corresponding to a macro state. Now, we will have to deal with this a little bit more in detail. Firstly, like I said, we are dealing with the molecular perspective of entropy. Secondly, when you hear the word entropy, you would often hear it in the context of some kind of randomness or disorder. Now, this idea of randomness or disorder for entropy does not come to us from classical thermodynamics. You have to resort to statistical mechanics to be able to appreciate why entropy is associated with larger disorder or larger randomness. Now, for that, what we will do is we will consider an analogy, right. The analogy we will be looking at is, consider that you have a jigsaw puzzle, Now, instead of these jagged edges, consider that you have square pieces. So, all you have are square pieces of the jigsaw puzzle, and let us assume that you are dealing with the puzzle of the Mona Lisa, which is a very famous painting, and let us assume it is a 100-piece puzzle. So, you have 100 square pieces of the jigsaw puzzle, which if completed right will give you the original Mona Lisa picture. Now, the question we ask is, in what possible ways can we arrange the pieces of the puzzle, and what is the probability that one of those arrangements will lead to the final Mona Lisa face? You notice that there is exactly only one way in which I can fit all those 100 pieces together to get the final and the only correct result of the Mona Lisa's face. But you notice that there are slightly more number of ways in which I can have almost solved the puzzle. In other words, I could have got most of the puzzle right. In some places, I could have switched the eye for a ear piece for the nose for the lip, etc. But largely, I could have got the puzzle right. So, you see, the number of ways in which I can mess up the puzzle to almost get it right is definitely more than getting the puzzle completely right, which is only one way. Now, if you take that to the other extreme and say, what are the arrangements of this puzzle such that I can completely jumble it up. So, I can arrange all the pieces of the puzzle, this 10 by 10 matrix if you will, and that should not result in the Mona Lisa's face at all. You notice that there could be a lot many more ways for me to completely jumble up the puzzle. Piece 1 can fit, what should go in as piece 1 can now fit anywhere else, because I am jumbling up. So, you see, the closer I am to finishing the Mona Lisa's puzzle correctly, her face correctly, the lesser number of arrangements I have for the system. The more further away in terms of completing her picture and the more jumbled up I get, the more the number of arrangements I have for the puzzle. Now, you go from 100 to a 1000 piece puzzle. Same Mona Lisa, now you have 1000 pieces. And you can again ask, what are the number of ways in which I can arrange these 1000 pieces in a matrix such that they are all jumbled up? You can essentially come up with thousands and thousands of ways, and you can count those numbers. You can count, they are associated with specific probabilities, but essentially, conceptually, you will see that there are thousands and thousands of ways in which you can arrange it such that the puzzle is wrongly done. But note that even in this case, there is exactly only one way in which you can get her face exactly right. So, even in the 100-piece puzzle, there is only one way in which you can exactly get her face right. Even in the 1000-piece puzzle, there is only one way in which you can exactly get her face right. But in the 1000-piece puzzle, the number of ways in which you can get it wrong in a jumbled up manner has gone up significantly. Now, you assume the puzzle has these many pieces. If I had to now practically deal with these pieces and still get the Mona Lisa's face, now you can ask, in how many ways can I incorrectly arrange these pieces from this very large 1 million pieces essentially, from this very large set, such that they are all jumbled up. So, in the jumbled up case, what should have gone as piece 1 has now many more options to go into, many more slots to go into as compared to the 1000-piece puzzle if I had to mess up the puzzle, right. And as I get closer and closer to finishing the puzzle, in this 1 million piece puzzle, there are lesser ways to almost complete the puzzle correctly compared to completely jumbled up. But note that even when you have 1 million pieces, there is only one correct way for you to fit all the pieces together to get her exact phase. Now, this sort of a digression might serve as a useful analogy for us to think about entropy. What we are trying to say here is, these puzzle pieces fitting together in different arrangements are what we are calling number of possible distinguishable microscopic spatial arrangements. Now, if these are molecules, for example, and if you take a box like this with molecules, there is only one way for the molecules to all cluster to one side. Whereas if the molecules had to find or disperse, so to speak, and that's one way to think about entropy macroscopically, which is it's a measure of the tendency or of the energy to spread out or disperse. So what you will see is, with time, if you initially had all molecules on one side, if you remove the barrier, all the molecules will spread out over time, right, and they will be in different positions. And that's because with time the entropy of the system has gone up. Now, if you come back and observe this system much later, you would be very surprised to find all the molecules clustering in one region. If you did nothing else to the system, this would not be something that you would expect, just naturally. That's not because it's impossible, it's improbable. The probability of this configuration occurring is so low that you might have to wait essentially the lifetime of this universe to perhaps see this kind of a state occurring on its own. Whereas the number of ways in which the molecules can be arranged throughout is so many that that is the more probable situation that will occur. This is not unlike only one way for us to solve the Mona Lisa puzzle completely, whereas a gazillion ways for us to mess up the puzzle. We are speaking now in terms of probabilities. So, two things come out of this idea. First thing is that we are talking about the molecular picture and the number of microscopic spatial arrangements of the molecules as a means to understand entropy, and we are assigning probabilities now to each of those configurations or states, microstates, and the collection of these microstates is typically called an ensemble. And you note that as the number goes up from, say, 100 piece puzzle to 1000 piece puzzle to a 1 million and so on, these are the numbers that these very large numbers are the kinds of numbers we will be dealing with in a real system of molecules. So, the probability of you finding all the molecules in an ordered state is far lesser compared to the probability that they will be more disordered. So, now you can perhaps see why the word disorder is used for entropy. It has to do with the number of arrangements with which I can mess up the Mona Lisa puzzle versus the number of arrangements with which I can get her puzzle exactly right, which is exactly only one way, whether I have a 100 piece puzzle or a 1000 piece puzzle or a million piece puzzle. Interestingly, entropy is also is related to the second law of thermodynamics, and that law again is sort of an interesting law because many other laws in nature are conservation laws. They all say that something is always conserved, mass, momentum, etc. Second law is one of those laws that says that something always keeps increasing, and that's again one reason why we find it a bit hard to grapple with the second law. And Arthur Eddington, who was a champion for Einstein in some sense, he is said to have remarked that if you do experiments and you find evidence contradicting any of the laws in nature, he would not be surprised. I mean, it's very unlikely, but it will not surprise him. But he goes on to add that if you find evidence contradicting the second law of thermodynamics, then he says, I have no hope for you. And he uses the word humiliation. He says that you have to sort of go into humiliation if you claim that you found evidence contradicting the second law of thermodynamics. Very powerful ideas from very powerful great men. But again, coming back to the idea of an entropy, what we are ultimately saying here before we proceed is to add that entropy can now be related directly using the Boltzmann equation to the number of such configurations. So, the more number of configurations the system can exist in associated with the individual probabilities, more the entropy of the system. And here we see that entropy change has to do with, or for mixing, has to do with change in the number of arrangements or the microstates available or the microscopic configurations available for the system. This is also called combinatorial entropy. Particularly in the case of mixing. So, having sort of qualitatively looked at enthalpy of mixing and entropy of mixing, now we will move formally to understanding mixing, but we will consider the case of the ideal solution for small molecules, which is a good starting point for us to eventually understand polymer solutions. And first, we will simply define a mixture as a system with two or more chemical species, and a solution as a homogeneous mixture of molecules, where a homogeneous mixture simply means that all the components are intermixed at the molecular level. One example of that is a polymer solution in a good solvent. So, these are definitions that we will take for granted. And the equilibrium state of a mixture, in this case a solution, being homogeneous or heterogeneous, depends upon delta Hm, delta Sm terms. So, this is delta H mix and delta S mix terms. Now, we consider the case of ideal mixing. Just as we saw for ideal gases, you can also have something called ideal mixing, where you consider two sets of small molecules that are mixing, let us say two liquids, where mole fraction and volume fraction are the same. For such a system, when they mix, for ideal mixing, the change in volume occurring from mixing, so delta V mix is 0. And likewise, we assume that 1,1 and 2,2 interactions are the same as 1,2 interactions. So, at the molecular level, in terms of the enthalpic contributions, the delta H of mixing is also 0, because remember that this is directly related to delta 1 minus delta 2, where 1 and 2 are the two components and delta is simply the solubility parameter. And if we assume that a molecule of 1 interacting with the molecule of 1 and a molecule of 2 interacting with the molecule of 2 is the same as the molecule of 1 interacting with the molecule of 2, then delta H mix is 0. Another way to think about it is, there is no real difference between a molecule of 1 surrounded by molecules of 1 or a molecule of 2 surrounded by molecules of 2 versus a molecule of 1 surrounded by molecules of 2 or a molecule of 2 surrounded by molecules of 1. They are all the same from an enthalpic perspective, from an interaction perspective, which means delta H mix is going to go to 0. So, from you look at from a free energy perspective, where delta G mix is simply delta H mix minus T delta S mix, this term has gone to 0. So, the only factor that determines the thermodynamic feasibility of mixing for such an ideal solution is the magnitude of delta S mix. And delta S mix is given by S12 minus S1 plus S1 plus S2. This is very common in thermodynamics, where the change is given by the after minus before. So, S12 represents the entropy of the system in the mixed state, S1 represents the entropy of system 1 before mixing or pure state, S2 represents the entropy of the system 2 before mixing in the pure state. Now, all we need to do is to determine the microstates here for before and after mixing, and that will lead us to calculate delta S mix, and if we know delta S mix, we can now access delta G of mixing and really tell if the mixing is going to happen or not from a thermodynamic perspective, for which we consider something called a lattice model for small molecules. So, this is to help us determine the number of arrangements or configurations which we need to access the microstates, which we need to access delta S. The premise here is very simple. The premise here is that a solution can be represented as a regular array of lattice sites, wherein each site can be occupied by either a solute or a solvent molecule. So, you have a lattice, an array of sites. Think of them as a checkerboard where you are placing different coins, and each site can either take a solvent molecule or a solute molecule. If you assume N1, capital N1 is the number of solvent molecules, typically 1, the subscript 1 is used for solvent. All of these N1 sites are occupied, N1 sites can be occupied by N1 solvent molecules, and if N2 is the number of solute molecules, where N2 solute molecules can occupy N2 sites, then the total number of lattice sites N0 is given by N1 plus N2. So, let us first consider the pure state, then we will look at the mixed state, because remember, we have to look at the configurations both in the pure state and in the mixed state to be able to calculate delta S mix. In the pure state, before mixing, you note that there is exactly only one way for us to arrange these molecules, and here we have to note one subtle point here. The microstates that we are referring to have to be qualified by the word distinguishable. One microstate has to be distinguished from another microstate, then only it is considered unique. So, here only one way for us to uniquely arrange the molecules. What that means is, if this is the solute lattice and if this is the solvent lattice, if I now consider 16 black balls or circles here and 9 circles, red circles here representing solvent and solute respectively. If I now replace this black ball with another black ball, you will not know the difference. So, in that sense it is not distinguishable. If I replace this black ball with another black ball, you will not know the difference because it is not distinguishable. Likewise here, if I replace this red ball with another red ball, you will not know the difference. So, it is not distinguishable. Likewise for this red ball. So, if you now take that argument to its logical conclusion, what you will quickly see is there is exactly one way that exists for me to arrange the molecules of the solute and the solvent in the pure state each. What happens in the mixed state? The mixed state is slightly more involved, because after mixing you can now ask how many distinguishable ways can we arrange N1 solvent and N2 solute molecules on N0 lattice sites, and shown here is just one sample arrangement where I have arranged the 9 red solute balls and the 16 black solvent balls on a matrix like this, and you very quickly see that this represents just one arrangement. Now, if I replace this red ball with another red ball, or if I replace this black ball with another black ball, that does not lead to new distinguishable arrangements. But if I replace this red ball with a black ball, then you will notice the difference. So, if I start with an empty lattice and I start arranging the red balls and the black balls, let us say from this set in the pure state, I can start adding, and as I keep adding, every lattice site gets filled, and I can have many such configurations. I can, let us say, go through and fill this entire lattice site with this kind of a configuration. I can refresh and start again and do a different arrangement where the red and black balls are again all mixed. The question now is, how can we determine the number of distinguishable ways of arranging these red and black balls on this lattice site, or how many distinguishable ways are there to mix the solvent and solute molecules in the mixed state from a microstate perspective. How many distinguishable microstates or configurations exist? So, that question is going to lead us to ultimately figuring out how to determine delta S mix. So, again we note that the number of microstates for pure solute and pure solvent in the unmixed state is exactly 1. There is only one way in which you can arrange the all the black balls in the pure state, all the red balls in the pure state. So, S1 and S2 will be k log of 1, which is just one configurational arrangement. So, the entropy will go to 0 for the pure solute and solvent case. That is not true in the mixed state. In the mixed state, you can actually assign probabilities and calculate what are the number of distinguishable ways in which you can arrange the solute and solvent molecules, noting that replacing a solute with a solute or a solvent with a solvent does not lead to new distinguishable configurations. So, that is what this is. This is what we have to calculate. We are not going to do the derivation entirely here. I am just going to show you the final expression, and I will give you a reference at the end of this lecture in case you are interested in looking at the derivation in more detail. We are now going to say that there are many different distinguishable ways for arranging solvent and solute molecules after mixing compared to the pure state, where in the pure state there is only one way to do this. So, if you can find a way to count that, and that can be done using probabilities, count the number of distinguishable microstates. Essentially, you are counting how many ways in which can I jumble up the Mona Lisa puzzle, right, if you want to think back to that analogy. And you apply the Stirling approximation, which is just a mathematical trick for us to get rid of factorials for very large n values. When n is very large, you can apply the Stirling approximation, and you will get rid of all the factorials that show up when you count the number of states based on probabilities. Ultimately, if you do that, you will end up with an expression that looks like this. So, this delta S mix is given by minus k, which is the Boltzmann constant. N1 is the number of solvent molecules, N0 is the total number of solvent molecules and solute molecules, and N2 is the total number of solute molecules. Now, if you recast this in terms of mole fractions, if you know the relationship between K and the gas constant R, they are related by the Avogadro number, then if you convert that into an R, you can now recast the capital N1 in terms of small n1, which simply represents moles. This equation recast in terms of mole fraction is given by minus R times N1 log x1 plus N2 log x2. Now, our work is not fully done yet. We have only calculated the delta S of mix. Right away what you can see is this term and this term will be negative. And if those terms are negative, there is also a negative sign here. Negatives will cancel each other out, and for mixing, delta S mix will be overall a positive term, and that, as we will see very quickly, will favor mixing. So, if you have to calculate delta G, which is the change in Gibbs energy due to mixing, this term is 0 because it is ideal mixing. 1 1 and 2 2 are the same as 1 2 interactions. So, if you simply substitute the expression for delta S here, you see that delta G mix is going to be RT times N1 log of x1 plus N2 log x2, and like I said, these terms will be negative, making delta G overall negative, and that mixing is favored for ideal solutions. That is a very important result that we will note here. Remember that this expression holds true for ideal mixing of small molecules where delta V is 0, delta H is 0, and delta S is given by this expression. Now, if you are interested in details of the derivations that we did not look at here to calculate this, here are some suggested references. A lot of the concepts we have already covered here. What we have not looked at is the mathematical steps involved in the derivation, which if you are interested, you can look at these references. They should not be very difficult to follow if you have some basic understanding of probabilities. So, with that we will end this lecture noting this very important equation and using this as a starting point later to look at Flory-Huggins theory for polymer solutions in the next lecture.